Okay, hi everybody. So in this video, we are going to continue working with magnitudes and inner products of vectors. And in particular, let's explore what happens when we take the inner product of two vectors that are perpendicular. And so by perpendicular, we mean that the angle between the two vectors is a right angle, like we have pictured over here. So let's consider vector u, which I've drawn in blue, and a vector v that I've drawn in green over here. And these two vectors we can see are perpendicular to each other. So if that is the case, then what I can see is that this vector in red over here, which we can think of as the distance between vector u and vector v, that is equal to the vector u minus v. And if I similarly consider vector v, but I go the exact same distance in the opposite direction to get the vector minus v, well, u is also perpendicular to minus v. And we can see here that the length of this side of the triangle, which is given by u minus v, that these two vectors that I've drawn in red, as a result of u being perpendicular to v, we can see that these two vectors have the same magnitude. So if u and v are perpendicular to each other, one quick result of that is that the magnitude of the vector u minus v is going to equal the magnitude of the vector u minus v. And it may be easier for us to therefore compare the magnitude squared. So this is going to allow us to avoid dealing with the square root. So if these two quantities are equal to each other, then applying the same operation to both of them, namely squaring them, then we still have equality preserved, that this quantity squared is going to equal this quantity squared. So let's see what might come out of this condition. So if I know that u minus v squared, the magnitude of u minus v squared, is equal to the magnitude of u plus v squared, well then let's start to expand these magnitudes. So I know that I can rewrite the magnitude squared as the dot product of u minus v dotted with u minus v, and that should equal u plus v dot product with u plus v. And now we can use properties of the inner product, a distributive property, to break these up. So I can take this line, for example, and say this is equal to u dotted with u minus v, so that's where this term comes from, minus v dotted with u minus v. And we can apply the same property to the right side of this equation to get u dot u plus v dot u plus v. And now we can use the distributive property another time. So on the left side, we can rewrite u minus v, the magnitude squared, as u dotted with u minus u dotted with v minus v dotted with u plus v dotted with v. And on the right side, we have a similar looking result. We get u dotted with u, but now we have a plus u dotted with v plus v dot u, and then finally plus v dotted with itself. And now we can use properties again. In particular, we can use the property that u dotted with u, that's the same thing as the magnitude of vector u squared. These should be bolded vectors. And v dotted with v, I can rewrite that as the magnitude of vector v squared. And we also know that the inner product is a commutative relationship. So u dotted with v, that is equal to v dotted with u. So I can combine these two terms and say that this is minus 2 times u dotted with v. So on the left side, we have the magnitude of u squared plus the magnitude of v squared minus 2 times u dotted with v, u inner product with v. Now on the right side, using the same properties, this simplifies to the magnitude of vector u squared plus the magnitude of vector v squared plus 2 times u inner product with v. And now we can simplify this equation, namely, if I subtract the magnitude of u squared from both sides, then these terms will cancel. Subtracting the magnitude of v squared from both sides is going to cancel these terms off, and then we can divide both sides by 2. And that gives us this equality that minus 1 times u inner product with v is equal to u inner product with v. So the only way that the minus 1 times a number is equal to that number is if that number is equal to 0. And so now we get this nice result that, first of all, if u and v are perpendicular, then it follows that the inner product of u and v, that should be 0. And vice versa, if the inner product of u and v is equal to 0, you could work your way in the other direction and show, therefore, that u and v are perpendicular to each other. So now we see a nice connection between the inner product and determining whether two vectors are perpendicular to each other. Namely, we say that two vectors u and v in Rn are orthogonal. So orthogonal is equivalent to saying perpendicular. So orthogonal means the angle between these two vectors is a right angle. So two vectors in Rn are orthogonal if and only if the dot product of those two vectors is equal to 0. So this gives me a really quick way to check whether two vectors are perpendicular or not. I take the inner product of those two vectors. If I get 0, those two vectors are orthogonal. If I get something not equal to 0, then those two vectors are not orthogonal.